Yeah, so let's talk a little about uniform circular motion, right? Um, it's talking about, and the topic mentions, okay, uniform, right? And let me explain why we say uniform, because circular motion is rather complex, right? Um, and we're saying uniform because we're going to talk about a body moving in a circle, and it is moving with constant speed, right? It's moving with constant speed. So we're going to call it uniform circular motion. And as I said, circular motion can get very complex. You can have variable speed, right? You can have a body moving in a circle, horizontal circle, you know. I think I'm drawing that wrong, right? So a horizontal circle. It can be a vertical circle, like you hear you swinging something around you, right? And this point is higher than this point, right? Yeah. Here, it's like when you watch it sideways, it's one level, right? I don't know if you've ever, maybe you have a little object here, and you're standing in the center here. Oh, and you're putting, and you're spinning this thing around horizontally around you, right? I don't know long ago, just to mention this, when we were kids, we never had water, and so you always have to go fetch water. Nowadays, y'all are very fortunate. Have so much water at your disposal. You wasted so much. Long ago, we didn't have water. So there's hardly a village you go to where you don't see kids all over the place fetching water. So we used to fetch water with anybody get a paint can. Um, people would paint their houses, and mind you, that's a treasure, having a paint can. So people would like take the paint can and fetch water with it, and bring it home in order to wash or wash wheels or wash clothes or you know, wipe out the house and so. So we used to take the paint can. I used to fill it with water, not full till it's overflowing, but kind of halfway, three-quarter, and tie a string on it, and we used to swing it around in a horizontal circle, and only to figure out that the water don't fall out. So the paint can is like, let me draw it. The paint can is almost like that. Water is inside, you know, and the string is here. So you are here with your hands, and how am I drawing that? Yeah. Right, yeah. And you're swinging this thing around you, and the water remains in that can. Y'all ever try that as kids? I mean, do you see people doing that now?
So nobody don't even know. The children don't do them thing now.
Yeah. Hey, listen to this. I have a class, a physics level 4 class where there are lots of youngsters inside. Probably they're all less than 20. As I have a test with them, they're all kids. They're probably, I think 17, 18. They don't know some high school, right? And none of them can figure out what I'm talking about with this paint can, right? I said we used to spin this paint can around. When you slow down, what happens? Um, if the thread, sorry, the twine that you tie there, right, or the rope, if it cuts, which direction the paint can would go, and so it's big trouble. I regret I used the example because nobody could understand anything. And our discussion was purely theoretical because they don't know what I'm talking, you know. I was using the same water situation, and I was telling them, when I was a kid. Oh, we were talking about uh, heat capacity and that sort of thing, right? And I was talking about, when I was a kid, we had the water. So before you go to school in the morning, I have to walk about more than half a mile away. There was a canal, and I used to have to go and bathe there. And you never want to go in the canal because you think the water is going to be cold because the place is cold. But if you were to get into the water, you realize the bottom of the water is very warm, and the top has a little coldness, but the bottom, just about a foot or two in the water, it's very, very warm. And we were talking about how that is related to heat capacity and all of that. I was telling them, okay, on alternatively, if you on a very hot day like today, you have a pool of water, you go in, the bottom is very cool, while the top might be a little warm. And you're talking about heat capacity and so on. Students just could not, for some reason, get what I'm talking about. Yeah. In some ways, those experiences, you don't want to have them again. But they taught you so much. Yeah, back to our discussion of uniform circular motion, right? So before we get into some ideas, some concepts that are related to circular motion, we want to introduce to you this idea of an angular velocity, because we spoke about linear, right? I think we talked about linear velocity early, right? When we did those motion equations and so, right? We talked a lot about the velocity and linear velocity and so, right? But now that we're going to talk about something moving in a circle, right? Maybe if this is the center of the circle, as you move from point to point, let's say you move from here to there, as you move, but if you're going anti-clockwise, right? Some angle is swept out, some angle is swept out as let's say a body is heated, and it moves along this circular path, and it sweeps out the angle. So we're more concerned now, or we're not just concerned with what distance it has covered here. That is important. But we're also concerned about what angle has been swept out in the middle there, right? So this idea of an angular velocity is becoming important, And basically, what really, when you talk about the angular velocity, what are we talking about? Well, basically, maybe we can let's say this is the origin here. Let's call that O, and maybe we'll call that P, Q, right? And let's say body motion here to there, right? So the angular velocity of P as it moves from here, from P to Q, right? As it moves from P to Q, is really the rate of increase of this angle, right? Which we can simply put as, we're going to call it omega. We're going to call it omega, right? And it's basically what? Angle that is swept out from P to Q over T. That's as simple as it can get, right? If the rate of increase, or of this angle here with respect to time as you move from P to Q there. What we want to actually do, especially how we're familiar, you and I are familiar with linear velocity. You know this good. You say, man, how is it related to this linear velocity? Is there some kind of relationship? And yes, we can actually come up with a relationship, right? Let me maybe maybe I'll use the same relationship. So from this relationship here, we get what? Theta is equals to omega t, right? Hmm? I'll agree with that, right? That ain't hard to figure out. Good. Now, the length of PQ, and I think you all did this in we did a course, MTA 1104, right? Where the length of our PQ is going to be what? I remember. I'm yeah, layman students that I'm trying to school. I teach the thing and then remember the thing and last everything and so yeah, self learning. So PQ will be equal to R theta. Yeah, remember that. That's if this like this is R, right? R theta. And we're measuring theta in radians here, right? R theta. You remember that? Huh? So basically the speed we said, the speed then speed is equals to R theta over T, right? The speed is R theta over T. You realize what this piece is? What this piece is? Theta over T. That, right? So if you watch here, the speed is the distance traveling. The speed, and here, I want to use the word maybe loosely. The linear speed, even though it's not really a straight line, right? Uh, but here we're talking about distance, distance. Instead of velocity, I'm going to change. I'm not using the word velocity, I'm using speed, right? Using speed. So theta, r theta over t is the speed. But we recognize that this theta over t is really this fellow here, omega, before, right? Is equal uh, uh, omega, right? You agree with that? Hmm?
Yes, sir. Yes, sir.
Mhm. Yes. Right? So um we're seeing how the two are related, huh? Right? And basically what we're saying here, while we're talking about speed, if we were to go back to the word linear velocity, if you were to move from here to here, this this velocity straight that is making like a tangent to the circle at that point, right? V is equals to R, right? So that's what we want to get. I know we were using the word speed to refer to, okay, the distance traveled over the time t. But we want to go back to the linear velocity, which is really, okay, when it's there, that velocity going that way. I wonder what's going on. Yeah. It's not a straight circle, just go draw itself like that. Yeah. That linear velocity V is equals to R. And there we get a nice relationship connecting what we know about this linear velocity here is related to um, angular velocity. That's omega by this formula, r omega, right? So we're gonna use this a little later on. So just keep it handy, and in just a moment, you'll make that connection, right? Good. So we're going back now to um, we're going back to our discussion of uniform circular motion. All right, and going back to our, now that we're introduced to this idea of angular velocity, we related it to linear velocity. So, you know, we kind of uniform circular motion. All right, so let's say something is going on in a circle. All right. So funny thing about it is that even though a body, all right, it's moving with a constant speed, and that's why we're calling it uniform circular motion. It's moving at a constant speed, meaning if you were to find the, let's say, all right, so, right, let's say, all right, if you were to, let's say the thing is going that way, right? If you were to check the linear velocity there, you know, don't, it just doesn't look like, yeah, yeah. They look more right, right? They look, well, let's say, okay. And as it turns now, body is here now, right? So it's V, right? Same speed, right? Or same linear velocity. You can be using them kind of interchangeably. Even though maybe I say a small angle, delta theta, you know, has been swept out, right? Let's say that. So a body moves from here to here, right? And it has swept out a small angle. I exaggerated the angle because of, so you want to draw anything like that, right? Now, even though the speed is constant, right, or the linear velocity is the same, the body is accelerating, right? So a body, right, basically that is moving in a body in uniform circular motion is accelerating, Can anybody say why? Because the linear velocity has not changed. I know when we're dealing with linear motion, if a body is moving with constant linear velocity, well then it's not accelerating. But can anybody say why we are saying no? This is new. I'm just telling you that yes, it is accelerating. Can anybody say why we're saying that it's accelerating, even though the speed remains the same? Look at the diagram going. What is changing as the body goes around the circle? What is changing?
So I believe that the direction is constantly changing.
Yes, correct, yes. So at every point in the circle, the arrows seem to be pointing in a slightly different direction. You see? So even though the linear speed is the same, the body is accelerating because it's changing direction. And why we are saying acceleration? Well, we did Newton's laws of motion, right? And when you think about it, this body, right? Look here. If there's no force acting, the body would not change direction. So it seems to be a force is acting, right? A force is acting to change this direction. So it's not, the body is not moving off at a tangent here. It's actually changing direction. Look, it's gone in this other direction. So that change in direction is really created by a force. And when we talk about F equal ma, force creates, all right, an acceleration. Right? So for that change of direction to take place, a force is needed and the body is accelerating, right? So the body is accelerating, which, well, if there's an acceleration, there needs to be a force, right? I hope I didn't say that wrong the first time I there. So the body is accelerating, even though it's moving with constant linear velocity. It is accelerating because it's changing direction. Right? But now we just said that for this to happen really, you need a force. Right? You need a force. So what's the size of the force? Where might the force come from? And that's what we want to talk about. Now, the acceleration, we can write it two ways, and there's a bit of calculus as to how it's derived, right? There are two expressions. The acceleration is measured by this expression. A is equal to v squared over r, or r omega squared. Even notice I sent you got all of this, right? And there's a bit of calculus involved as to how you get from this little diagram straight to the acceleration, right? There's a bit of calculus there. It goes back to that same, I don't know if you remember from your MTH, I think it's 1204 where you do small angles and you approximate sine delta theta to delta theta when the angle is very small, right? I mean, all of that, but I'm not going to get into it, right? But there's a little bit on that you have to use in its own derivation. Right? You could always check that in. And you end up with your acceleration being v squared over r. And remember we related v squared, I think what we got? V equal r omega or something like that. So if you take that, this here, put it on top there, do some canceling out and say you'll get r omega squared. Right? So the acceleration can be written like this or like that, right? And then that brings us to this question of, well, okay, if this thing is accelerating, really the acceleration is acting in here, right? Through here. Yeah. The force is also acting that way. There's a name to that force. They call it the centripetal force, right? And that is the force that keeps a body moving in a circle, right? So for us to keep a body moving in a circle like that, we need some kind of force, you know, kind of tugging at this body so that even though the tendency, according to one of the laws, is to go over the tangent, no, it's kind of tugging it, pulling it in this direction. It wants to go here and go over the tangent, no, this force is tugging it and, you know, kind of tugging it, and it's coming this way, and so on and so on and so on. So that force is referred to as the centripetal force.
Sorry, just a question. Let's say we tie a piece of let's say stone on a string, right? And we spin it. It will go in a circular motion, right? But where is that centripetal force acting? Is it acting on the body itself, or is it acting on the at the point where your hand holds the string?
Well, that is the reaction to you. Okay, you are exerting the force, right? So when you exert the force, that force is okay. It's acting on this. Well, it's acting on the body going in a circle. But remember, you feel a reaction in your hand, right? You
Yes,
get so you create a tension in the string. Let's say the string, right? You are actually creating that tension in the string that is kind of moving this body in a circle. Now remember, that is going to get a reaction now on you, right? You are here. So what you are feeling is really the reaction force. You do feel something tugging at you as well, right?
Yes, sir.
So it's both. The force is acting on the body, and the body, well, the reaction of the body, right, is acting on your hand, right? Well, in terms of Torladi, right? Action, reaction.
Yes, sir.
Notice though, it's all being transmitted through the string, right? String
Yes,
that
sir.
you tie it in. You
Okay.
are transmitting the force that you are exerting to the body via the string, and the body is transmitting the reaction via the string, right? Um,
Yes, sir.
so you do feel something in your hand, right? And when you ease it up, you talk about spinning something in your horizontal circle. You have a vertical circle to spin something into, right? Uh, if you slow down, you notice that what happens. Um, the circle gets smaller and smaller and smaller. Okay? The body just hangs.
Yes, sir.
Right?
Just
Then you stop exerting that force, or you kind of reduce it to the point where the body stops. And all that you feel in your hand now is the weight of the, let's say, a piece of brick on the string, the weight of it, you're feeling it on your hand, right? And the reason why is that when the force is acting down, that force is transmitted via the string to your hand, right? And well, it's just a reaction force you are feeling. Yeah.
good.
So just remember this name, and you're going to hear about a related force called the centrifugal force, and that's what you're feeling, CR. The centripetal force is what you are exerting on the O. Let me put in that word here. What? Centrifugal. I don't use these words every day. So I hope I get this spelling right. I think that's it. Centripetal force and centrifugal force, right? One is the action, the other one is the reaction, right? And I think, well, it's a good thing you mentioned that, Sina. It's a good thing you mentioned you're feeling something on your hand. And you want to know where really the force acting, really, your force that you are exerting, that is acting on the body, that is spinning, is a centripetal force. Now the body is going to react, right? You understand? And it's going to produce a centrifugal force, and that's a pulling you feel on your hand. And hence the question you're asking, right? You are exerting force on the body, the centripetal force. That's what keeps it going. The body reacting to that now, Newton's third law, with a centrifugal force. That's what you feel. That's what you feel. Yeah. That's interesting, right? And later on, we are going to we are talking about the motion of satellite, and you see how important this centrifugal force is for the Earth when it comes to the moon and the Earth. Remind me if I forgot, right? Remind me to talk about this centrifugal force, right?
Yes, sir.
That the moon is exerting on the Earth as well, right? That reaction, like, and how important it is. Good. So we talked about the acceleration, name the forces that are involved. Yeah. Good. Now, circular motion, as I mentioned, well, we're going to stick with the speed being constant always, right? And we're going to stick with like something going, let's say you have like a horizontal table, let's say a table, and maybe something spinning on the table. I don't mean to show it that way. It's on the table going in a horizontal circle, right? Or you can actually have a body, maybe your hand is here, right? Your hand is here. You have a string attached to it, to a ball, you're spinning it in a horizontal circle. You can stick with those simple examples. So tension here.
Or we can use the roulette board as an example here.
Oh, great example. Yes. And this tension and this string like that you have here, if you resolve it this way, that's what keeping the body in a horizontal circle. There is a vertical circle. I'm not going to get into it in this piece. There, if you like, I told you about that can with the water, right? We actually spin this thing both in a horizontal circle as well as something you hear, right? and you spin the thing around you, you know, you spin the thing almost in a vertical circle. It's not exactly up. But you actually spin it in a vertical circle. And the dynamics is a little more complex. Because when the body is at the bottom here, right? You find that the weight plays a role. But when the body is at the top here, right? Sometimes you see situations where a little bit of water comes out, right? Because the force you're spinning it with is a little, sometimes it's not sufficient to keep the water. The centrifugal force is not enough to keep that water in the can. And sometimes a little bit is fall down. And can anybody say, how do you keep the water in the can at this topmost? I know I said we're not dealing with this, right? But what keeps the water in there? What can you do? I know you haven't done it, maybe, but what do you think you can do? I remember we have to do that to keep the water in there. What keeps the water from falling out at that point? What you need to do?
So you keep it at a constant speed?
No, it doesn't work like that. No.
So I've spin the thing before, but like I didn't really know what really causing it not to come. Like,
Yeah, you're like everybody else. And
Sir, is it because of inertia? Because there's
that plays a role. But how do you keep that water in there and it doesn't fall down?
Sir, I think when you spin this container with the water, there's a force. When you spin it, there's a force acting upwards in the container.
Yes. So what you want to do with that force?
Sorry, do you want to keep that force? I think it's gotta be constant, because if there is a small change in the velocity of the spinning of the container, I think, I'm not sure. I'm just saying, I think they will spin.
Maybe you do a trial spin and water falling out. So by the time you go on a second time, what you want to do to keep the water in you? Increase the speed or decrease the speed?
You have to increase the speed, sir. Spin
yes,
harder.
Increase the speed. And really, the increased speed comes from an increased force.
Yes, so if you increase it, yes.
Yes. So while the centripetal force is pulling, what is happening? It's pulling at the bucket. The reaction of the water is acting that way. It's equal to this, right? So if you see water falling out, if you increase the force down, the force acting up here is going to increase as well. Keep the water in. Yeah, I never regret those experiences in a way,
Oh, so they teach you a lot of things.
Yeah.
So, sorry, is it to just clarify the point, right? So gravity has no business keeping that water. It's just because of the force acting upward.
No, gravity has a role because your force now, the force you are exerting here, that'll be enough, right? Remember, you said this force, the centrifugal force, centripetal force, and this is the centrifugal.
Yes, sir.
So this depends on this, right?
Yes,
remember, the weight of the water when it's here is mg. You gotta make sure that this centripetal force is greater than mg, or else the water will fall on your head.
yes, sir.
Yeah.
Or the container will fall or something.
Yes. So yes, gravity has a big role to play there. But you gotta offset gravity. Right? You gotta make sure the force you are exerting, right, is far greater than the gravity, the mg, which is the weight, so that the water remains in the container. Yeah. Yeah. And then we'll talk a little about something you see on the roads. I don't know. All of you pass, I think, all of you pass the Palmyra Junction here, where I live. Y'all notice something when you turn around the Palmera there?
So as you turn as a vehicle turn, basically you go the direction of the vehicle turn for.
No, I'm talking about the level of the road. Y'all notice something when you
Yeah.
come to the Palmera turn? You see it around the Palmera turn here, you see it at the C-way of the turn.
Yeah, it tilts a little bit.
Yes. Let me see if I can draw that for you. Yeah, it's tilted somewhat, right?
Yes.
So, okay, the road is coming around. The road is slightly tilted, but I exaggerated a bit, right? So, um, so this is, I'm putting this on your car. And anybody knows why they do that?
So I think so that if the vehicle going and turn, he able to turn smoothly without having to use his steering a lot. They have to get a gradient in such a way that when it turn, that the vehicle can move smoothly through the turn.
Oh, you think so? All right. Maybe you're making some sense here. Let me say, okay. So you have a flat road, right? Let's just say that road that you have there. A flat road. Y'all know. Only yesterday I was going across that road. And my neck don't give me justice. So I watched this side and see it's clear. My wife was in the front seat. She watched that side and the road was very clear. And she said, you can go now. And as soon as I press the accelerator to cross the road, guess what? Somebody flattened out along the turn there, nearly crashing the road. Now, when you do that, right? If you are on a flat road, so you're banking the turn, right? Banking the turn coming along, right? Well, if this road was flat, what's the force that is keeping you from sliding off and just fly off the road? What's the force? Don't overthink it. What's the force that prevents the tire? So when you're coming around the turn, don't you feel something like telling on them tires this?
Frictional force.
There's a force seem to be kind of pulling you off the road. And the tire, something on the tire there on the ground has to actually kind of keep that vehicle on the road. What's it?
Frictional force.
It's a frictional force, right?
Yeah.
Between the tires and the ground.
Yes, sir.
That's the only thing that your vehicle seems to be pressing going out here, right? And the friction between your tires and the ground is acting in this way, right? So that is all that is helping you to come on that turn, that frictional force, and therefore, and that actually that force that is acting out here, this force here, we call it P. This is increasing with speed. The more fast you come on the turn, that force, like kind of wanting your car to fly off the road, is greater. But then remember, friction only have a certain what we call a limiting value. Friction can only be so much between rubber and concrete or asphalt, right? So if P is greater than F, you know what happens? You fly into I think Bosky or one of them guys own that house. You know how many run off there? You all notice some guardrails there. So
Yes, sir.
what they decided to do is to make the road slant like this, right? And when you make it slant like this, there's a force, all right, you all know mg, what's it? Mg, all right, this way will be mg, what's it, cos theta, right? So in this angle here is theta. And what's the force acting in that way? All right. Sorry. Let's just see. Oh, I'm not going down. Yes. force acting down there. What would this be? mg sine theta. Right? So this force is going to help you, it's going to help the wheel, the frictional force acting this way. So this is going to help that. Right? You get it?
Yes, sir.
Yes. So basically now this force is going to have a, I can even put it like this now. If you were to look up in the air, let's say you have like, I don't know how to illustrate it. If you were to, from an aerial view, this force here, right? And of course you can take this and resolve it to see if you can get a component, right? No, forget it, because this wouldn't have a, this is 90 degrees, this wouldn't have a component to it. This force here, mg sine theta, right, is going to have a helping effect on your frictional force. So whatever, you know, is acting out there, that centrifugal force P, is going to make you fly off your way, right? This here is going to help that. That's why they bank the road there. They do a column, they bank it. They kind of slant it a little. You see it both at the Palmyra turn here, and you see it at the Seagull turn. You know where else I think, see it? You know where Nanta saw that MPG place there? Just before there. There's a big turn there. Do you notice it?
The Tarlogy turn.
Do you notice it?
Yeah, it's very steep.
Yes. And you see the signs behind it now, huh? You see the sign behind bank tracks. And we're gonna look at an example or so. As a matter of fact, we're gonna come up with a formula as to the maximum force, right? Sorry, maximum velocity you can be going around a turn based on the angle, this angle here. There's a formula, let's see. I don't think this is in the notes. V equals square root of RG sine theta. Right? So you notice the angle plays a role. Right? Not too much of a role. Notice it's sine theta. So the smaller the angle is, sine theta is very small. It's just a couple of degrees, right? So the radius of the, if you were to take that banked part of the road and make it into a big circle, you'll pick up the radius. Well, G is G. Angle is the angle of the, how banked the turn is, right? And that will tell you, notice it's not much, right? It's not much. That will not give you license that, you know. Source said that the road banks are just speed, you know. When you think of all that's happening here, right? You're signing the angle and you square rooting it, so it doesn't give you license to fly around the turn here. As in many days I'm here at home, and you hear blah blah on the road. I have come to the point where I don't go because it's too common. The only time I went out was I remember one time. There was a guy, okay, this guy came from outside. And I think he brought a new car. I don't know if he bring it or he buy it or whatever. So he's on the Palmyra Road, he stopped the car on the bridge, left the keys and so inside, and he's going to open his gate. Not knowing that there's a couple of guys in another car just behind, trailing him. So as soon as he stopped, and he's going to open the gate, he's fiddling with a padlock. One of the guys ran out, jumped in his car, reversed, and started to speed down the path. In the haste now, he's coming around the Palmyra turn. He's forgetting that he can only, and with the speed he can go up with is the square root of RG sine theta. But he's doing, he left out the square root. Right? He's probably doing RG sine theta only. Right? Bladam, not a post. Well, the only reason I went out that because when he hit the post, That's a pose that brings overpower to the whole of number two and Vampire. The whole place went black. So we ran out. We went out and when we went out now, guess what? The guy wasn't so badly injured, right? So he said, wait, he go to the hospital, he left the car, jumped in another car, gone. Oh, by the way, the car that his friends were in, they got away. They didn't even know that he was behind made this big accident. They left him. So if he was next to that, he would have died. Anyway, he jumped out. We didn't know he stole the car. He just jumped in another car. Said, try driving to the hospital, I gotta go to the hospital. And he went away from the scene. Only to figure out about half hour afterwards that it's a stolen car and they got away from the scene. You know, so if he had known this formula, maybe they were back now. Yeah. So we're gonna look at some examples and so with all of these. You know, the motion on a flat surface where it's just going along in a horizontal circle, maybe like a conical pendulum. We actually where you have a string and you're spinning this thing in a horizontal circle. Look at that. And band tracks as well. We're gonna look at a few examples and so right. So that we can get a feel of the mathematics behind it, you know? Yeah. And then I want to talk briefly about what is this thing? The motion of satellite. The motion of satellite. Let's see if I can find an example or so that we can do. Take this question, let's try. I can't write it out on the screen, it's too much. Take this little question, let's try. So this is the particle of mass M. Oh, no. Let's take this one. This is a car example on a horizontal road. Sorry about that. Take this one. A car of mass M, I use capital M, car of mass M is turning a corner of radius R. You can use common R. A car of mass M is turning a corner of radius R. The coefficient of friction between the wheels and the horizontal road surface is mu. Notice that they didn't give us numbers, right? And I am doing this because I want you to compare this with the other formula we got.
So can you go back from after between the wheels and the horizontal surface?
The surface is mu. The coefficient of friction between the wheels and the horizontal road surface is mu. Not the Greek letter mu. What is the maximum speed? What is the maximum speed at which the car can turn the corner without skidding? What is the maximum speed at which the car can turn the corner without skidding? So here you have like a road that you can say that this part of the road is like part of a circle, right? But there's no banking. You didn't bank the road. The government, let's say the engineer don't know about band tracks. He got to be from Guyana. He didn't know nothing, the physics behind, turning a corner. So he just make the road flat. So what is the maximum speed at which the car can turn the corner without skidding? You want to take a minute and see if you can make an attempt, and then I'll write
sir.
out the solution.
Yes, sir. It
Take-
was few
Huh?
minutes. It was few minutes. I will attempt it and
Yeah, I'll give you 5 minutes. I'll pause this recording as well. Yeah. So for a flat road, we got this. And for a horizontal road, let me bring back the whole problem this way. Here. Right, so from the vertical cross section, we got this equation. And from above, like if you're looking at the road from above, right? It's not as road to say the road is circular. You're just like saying where you're driving is this piece here. Or maybe here to here. But just to relate it to circular motion, we draw a whole circle. And we're saying that the frictional force is all that is keeping this car on the road. Right? So the maximum limiting friction will be mu r. That will produce a maximum acceleration, or that can only offset a maximum acceleration of v squared over r. So that force that is going to be, causing this car to fly off the road must be equal or less than the frictional force. So you put it equal. You rearrange it so you get v, and you should get v equal mu r. I was mentioning that v equal square root of mu r g. Did I say mu r l? Mu r g. That's for the flat road. And what did we get for a bank road? V equal for a bank road. V equal what? Square root of, what did we get? I think we got RG tan theta. Wait, did I have sine theta or tan theta? I think I wrote that wrong earlier in the recording. Wait, let me see. I wrote that wrong. No, sorry. This is not sine theta. This has to be tan theta. Tan theta. I'm dead wrong. What happened? I have disconnection between my brain and my hands. Yeah, it's supposed to be tan theta. Yeah, so for a flat road, it's mu RL. I'm saying mu RL. Why don't I say mu RL? Mu RG. Whereas for a bank road, you get RG tan theta. And notice that basically eliminates the coefficient of friction. Doesn't play a role here. Right? Coefficient of friction doesn't play a role when the track is back. That's interesting. take one that involves a conical pendulum. That'll be the last one for that. So you have a, you know, take this one, see if you can. And this has numbers inside, right? This one has numbers inside. An inextensible string of length 2 meters. An inextensible string of length 2 meters is fixed at one end A and carries at its other end B a particle of mass 3 kilograms. That's a lot of weight.
Sir.
Yeah. Mhm.
Slow down a bit, please.
Yeah. So an inextensible string, 2 meters length. The length of the string is 2 meters. Is fixed at one end A. Yeah, you attach a string to an end here.
Yes, sir. At one end A.
And carries at its other end B a particle of mass 3 kilograms. Which is rotating in a horizontal circle. Which is rotating in a horizontal circle. Whose center is 1 meter vertically below A. Whose center is 1 meter vertically below A. They want you to find the angular velocity of the particle. Find the angular velocity of the particle and the tension in the string. Find the angular velocity of the particle and the tension in the string. So let me just draw maybe an idea of what I'm talking about. So you have this point E. There is a string attached to some mass here, right? And this is 3G mass. And this thing kind of going wrong in a circle, right? So this circle, what is this? 270. This is 1 meter. Right, so this is 2 meters. This is 1 meter. You can figure out this way, right? Think you're writing after the end. Right, so there's some kind of tension here that is, keeping this thing going around in a circle. So I think you can resolve that down here. You have to get an angle here. Right, there's some angle here. Yeah. Any ideas? Anybody getting anywhere? Hmm? There's something, huh? So if I'm to resolve this way, this tension here, right? So T, what are you, cos theta? The T cos theta is equal to 3G, right? So you can probably call that or force equation, you know? But I think they want what? They want the tension and angular velocity. So we got something with tension here, right? I think almost right here, you can actually calculate T. You see that? Because you can find the angle. Look, you got the hypotenuse is 2. You got this side is 1. So what that sounds like? Cos theta equal 1 over 2. And you can get T from that. Hmm? Hmm? T gonna be equal to 3G over half, which is what 6G is gonna get I'm getting tension in the string there, right? So yeah. And if you were to look at the thing, all right, like a horizontal circle. Let's see if I can. Yeah, there are horizontal circle. Like we're watching this thing from the top now. You know? Watching the thing from the top. Oh, my circle here. Yeah. Right? I see the thing spinning around like that. Here's only the object is spinning around. So there's a tension that will be T sine theta, right? And remember, you want the angular velocity. So you don't worry the linear velocity. Use the angular velocity. So the angular velocity, well, the acceleration, in fact, will be r omega squared, right? So this tension is producing this acceleration, right? So T sine theta equal to, I think the thing is 3, right? 3 kilograms mass, 3r omega, 3r omega squared, right? You can actually, well, you know T already. What do we have to find? We can know sine theta. We can know r, right? You can do all of that. And I think when you finish doing all of that, you should come up with omega is equal to square root of G. See if this is what you get. I hope I get it right. Yeah. Square root of G. And you fool around with everything. Yeah. So this is the last bit of application. We talked about circular motion and a horizontal circle. We talked about a bank track. Well, the one with the conical pendulum is also a horizontal circle. I think the last bit that the course outline mentioned is how we apply the whole thing to satellites in orbit, right? Now, I mean, I know this is a more let's see, oversimplified treatment of satellites in orbits, right? So don't attack me. It's not as simple as it seems there, right? Yes. So y'all would know that when satellites are placed in orbit, by the way, before we go there, y'all know that the speed that the Earth is rotating at. Let's just go there first. Anybody knows or can calculate it quickly? What's the rough circumference of the Earth? What's the rough circumference of the Earth? Type it into Bing or one of those things quickly, one of you. And divide it by, do it in km per hours, right? Km per hour, just to get a rough value. Tell me what it is.
However, sir, 40.0 meridianal circumference. Earth is only 40,675 kilometers.
But I'm hearing too much.
Sir, 40.75.
40, all right,
40.075.
So you're saying roughly 4,000.
So 40,075 kilometers.
Or yes, 40,000. So you're saying 4,000 km divided by 24 hours, right? Yeah, 24 hours. Give me a number here.
1669.79.
All right, roughly 16,000 km per hour. Y'all, y'all realize the speed of the Earth as it rotates on its axis? 16,000 km per hour. These are the kinds of things that make me religious. These are the kinds of things that make me right away believe that there has to be, some greater mind behind the Earth and the universe. So here is our planet spinning at 16,000 km per hour. I don't think none of you knows any vehicle that moves this fast, right? We got to be charged for speeding. Why our hair and so don't blow up? Because I mean, when you're driving at 100 km per hour, your hair blowing up in the car. Why that's not happening to us? Huh?
Sorry, I would say gravity, but since we're being religious, Lord, so sorry, maybe the creatives set it out so far because we're supposed to be tumbling at how fast things are going.
Why that's not happening?
For gravity.
That's gravity?
Not gravity keeping us stuck. Or maybe it's too fast that we're not going to feel it.
What? Okay. It's too fast so we don't feel it. Anybody else would like to take a go at it? I notice a lot of people dropped off. Anybody would like to take a shot at it? Why our hair is not flying away, and things aren't flying away with this speed?
Sir, I would agree with Miss Court. I think it's gravity. Gravity basically pulls us down, or is acting downwards. So we are planted on the ground, hence our hair, everything will be normal, just like everything, because of gravity. If gravity wasn't there, well, probably we'd be tumbling and all of the hair and things stand up straight,
I wouldn't tell you, right?
Sir, could it also be the force that is acting on us in different direction? So again, I tell you, I'm not a science person, right? So this is just me, my little imaginations going. Maybe the different force acting horizontally and vertically, and it's pulling all around, so it's kind of balance out each other.
All right. I'm not telling you. I'm not the answer key. I told you that. I wouldn't tell you. You figure it out, right?
But I don't believe it's that, because remember the amount of force that
you mentioned
exert on the ground exert it back. That's why we are stable. So it can be the amount of force that working around us or on us. Got to be somewhere around gravity court. You were right the first time. I would say.
All right. You think about that.
Or
Right?
do I have a point here?
Huh?
Do I have a point, a valid point here?
I don't think so.
Okay, so
Wow. Now think about it, yeah? Yeah, so imagine the Earth is spinning at that speed, right? Now, if you were to put a satellite, at a certain height above the ground, notice in the diagram here, right? So the Earth is spinning at 16,000 km around, here. So if you put a satellite up here, you all hear of what you call geostationary satellite. You all heard of that?
The what satellite, sir?
Geostationary.
Nope.
You never heard of geostationary. All right. Okay. So sometimes you look in the night sky and you see some satellites moving, right?
Sir, those are the things that look like shooting stars, right? Them little red lights.
They're not shooting stars.
So when you're small and you're looking outside, you just think everything is a shooting star. But there's some little red light like those move like at night inside.
Yes. No, not red, they're red.
So as a child, is how it look. So this how it look.
Yeah, don't look red. It's either you and I or I colorblind. It's more like yellow. You can think it's a moving star because it's the same color of the stars. At least that's what it looks like to me. I could.
Yes, sir.
Good.
So it could be me because sir, when light affects my eyes, sir, I just got squints. I probably saw probably me.
Good. So actually, those satellites move even faster than the Earth. That's why they seem to be moving. The geostationary satellites are actually moving. Well, don't forget, it has to be moving faster than the Earth because watch. Remember, if you have a satellite out here, and for this here, for somebody standing on the Earth here, to watch this satellite, right? To make it appear stationary, that satellite has to be moving even faster than the Earth because it has to cover this bigger distance, right? It has to cover this bigger circumference here within the same time. So the satellite has to actually be moving faster than the Earth, but really and truly, for an observer on the Earth, it has to be moving like the same speed of the Earth. So really and truly, it's not that it's moving 16,000 km per hour. It has to move much, 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 much faster than that, right? For it to appear stationary, because it has to cover that a bigger distance in the same 24 hours. So anybody watching at it, it must appear as though it's stationary. They call them geostationary satellites, right? And well, there are thousands upon thousands of satellites up there, you know, thousands upon thousands. And I don't know if you ever wonder, well, what keeps them up there? And mind you, they have satellites up there since your grandmother was born. And the question is, what keeps them up there? What keeps them up there? You ever thought of that? Do they have fuel up there that they're using? Let's take the geostationary ones. Do they have fuel? The fuel is supposed to run look how long, right? Unless they have nuclear power. Really and truly, what you're seeing, if you're watching let me see, let me make this even bigger. Yeah. Yeah. If you watch the equation here, is the gravitational pull of the Earth. Is the gravitational pull of the Earth that is keeping them in circular orbit, right? And that force is given by, well, the gravitational constant multiplied by, well, the mass of the satellite times the mass of the Earth over the radius, you know, that's the radius from the center of the Earth to where the satellite is squared. Now that has to produce the force that keeps that satellite in place. mv squared over r, right? So the gravitational pull of the Earth has to produce that force that, or the centripetal force that keeps the satellite in place, right? When we now, the question is, well, how do you get the Earth to do that? How do you get the Earth to just, you know, like when we were talking about you tying up that string onto the can and keep spinning it around. How do you get the Earth to act like that? As though the Earth attach a string to the satellite and is using its force to keep it spinning. How do we get the Earth to do that? Well, the key, and here is where, you know, those guys at NASA, you have to really admire it, right? You have to really launch your satellite at a certain speed, at a certain distance away. So depending on which distance, how high you get a satellite, you have to give it a certain velocity to start in, right? And once you get it to that height and give it that initial velocity, the Earth will do the rest with the force that is pulling it around. Now let's start with R. Anybody think, what is something you have to consider with R? Any thoughts? Okay, what happens to, let's say, somebody go to space and they're coming back to the Earth and they're falling through. Oh, you talk about, you just know, correct. You spoke about like a shooting star. You know what's happening there? You know what's happening? You know, it's shooting stars.
Or
What's
I think,
really
I think it's a meteorite or something.
Yes, sir.
What's
That's
happening to
for-
it?
Sorry,
What's happening
guys.
to it?
It's dead or something.
It's falling in.
Or
What
it's
is-
falling out its, or it fall out its place, or the natural
What is
place it
happening?
was falling.
What is happening to it as it falls through the atmosphere?
It burns. It's like blazes or like fire.
Yeah, it's burning up, and therefore you can't place a satellite moving at this speed here, 16,000 or more. Remember, I told you it has to be much more than this, right? You can't place a satellite moving at 16,000 km per hour within the Earth's atmosphere. It's gonna burn up, melt the steel and make it on powder. So you have to put it at a height that is greater, right? than the atmosphere. You have to come out, you have to break out there of the Earth's atmosphere, right? And it has to go out in what they call space, right? And they have different levels, and so they have low-level satellite, and you almost read about it, right? It's something interesting, right? And don't think that, well, I'm going to teach this thing, and therefore I don't have to know. The other teachers, people look up to you, and you must know stuff. You must be able to talk about stuff. And here, let me tell you, part of your, when people look at you, they think that you know so much, even though you don't know much. So you almost find out about these things and be able to talk about them and dazzle the children in the class. You understand? You got to inspire them. You understand? So you got to get, the student can ask you that, how, if the Earth is moving at 16,000 km per hour, why isn't our clothes flying off us and all of that, You understand? People will ask you that. So, we will tell you. Right? Yeah. Back to this. So you got to ensure that you are out of the atmosphere so that as you are flying around with this speed, as I said, much greater than 60,000 km per hour, that the satellite doesn't burn up because of oxygen and these other gases in the air. There must be no air there. It has to fly in space. So you have to ensure that R is the right value. But you will notice that the farther out that you put the farther out you put the satellite, the force, you will notice that this fraction, G M subscript E over R, gets smaller, right? You all realize that? Oh, and by the way, R is couple 1,000 km and so, right? So you almost find out, well, okay, what range R does take on? What value R does take on for satellites? Just throw that in Google, Moodle, what do you call it? Bing or Bard or ChatGPT. Of what order is R? Let me not tell you that you should find that out. And then you will notice that GMO subscript E divided by R will become smaller as R gets bigger, if you realize, right? That's the denominator. R is in the denominator. So the farther out you put a satellite, the less velocity you will have to give it, right? That starts, so it will keep going around and around for time indefinite, right? Yeah, satellites do have almost an infinite lifespan, right? Really and truly, its lifespan depends on well, the electronics it's made of, its hardware, and how long it will last and so on. Yeah, let me not get into that. Yeah. So the farther out you put it, the less velocity you will have to give, if you understand the math there, right? Yeah. But of course, to put it that far out takes even more work, right? You understand? And thankfully, there is where you all have to admire people like Sir Richard Branson and Elon Musk, right? The guy that owns Tesla. All the years in there, NASA was actually taking fuel. So much fuel. And if you see fuel that got born to take the spacecraft, right? The satellite into space. And what these two guys are doing is saying, no, why are you doing that? They take an ordinary looking plane, right? And they fly it up to a certain height, right? As high as they can go. So you don't have to use, big rockets and so to do it, to achieve that speed. They fly it up to a certain speed. And when they reach a certain height, then they launch it with the required speed, right? So they have found a much, much, much cheaper way to take satellites and even people and so to space. As a matter of fact, they've gone to the point where they're reusing when they fly out there, the spacecraft that they use, they go and they orbit the Earth and so, and the spacecraft comes back into the atmosphere and they actually use it back. NASA used to, and they to retrieve the thing and so, NASA used to say, "Man, thing born up too bad, you're good for what now you're left with millions, if not billions, dollars a waste." But what Elon Musk did is when the thing comes back into space, the Earth's atmosphere, it flies like a normal aircraft and it goes and it lands. the people actually using that same thing now, like a plane, you fly to America, you don't travel the plane, you reach America. You take that same plane, fly back to Guyana. Well, Elon them and so Richard Branson, they actually have gone to that extent where they're reusing the spacecraft. Until now, what NASA is doing is just hiring Elon them and Branson and so, and giving them the contract. Here, y'all do it now, y'all will get up. Yeah, so basically, my point in all of this was that the force required to keep those satellites, the centripetal force, is supplied by the gravitational pull of the Earth, right? But you have to launch it at the right R, right? Distance above the Earth, and at the right speed, right? Once you get these two right, you are right. So that's where you have to plan your R, and you have to make sure that the power of your engine can launch. If I want to shoot out from here, let me say Guyana here. No, don't let me say somewhere. You fly off, you have to launch it at that speed and shoot it now. So the velocity when it goes up there, it goes up in a curve. And when it launch, it has to be that V, this V here. V, the right V. And when it reaches here, it must get a right V. And it'll keep going round and round the Earth. Well, theoretically, you can go on like that forever. So that's that little bit here. You almost do some reading on this material here. Right? And do some finding out, man. What's happening here? This thing is crazy. What's going on? Taking long for you. Yeah.